Alright, in this video we're going to take a look at some of the problems from the worksheet called the mole calculations with unit multipliers. You can see question 1 has been done there if you want to double check your own answer. But let's do question number 2 together. If you think you know what you're doing, pause the video and try it yourself, or just check your own answers. So how many atoms of sodium are present in 10.0 moles? Well, right away I know that this is going to be a huge answer, because I know that 1 mole is Avogadro's number of atoms, so there'd be 6 times 10 to the 23 atoms in a mole. So 10 moles, I could even do mental math and say there's going to be 6 times 10 to the 24 atoms of sodium. But let's jump in and set it up with a unit multiplier. So we have 10.0 moles of sodium. And the question is, how many atoms is that? So we'll get rid of our moles of sodium and we'll switch to atoms, remembering that sodium is an element that is atomic. It's made of atoms. Therefore, 1 mole of sodium will have Avogadro's number. Now, if you know Avogadro's number for sure, then you can simply use the symbol capital N subscript capital A to represent Avogadro's number, and be sure you use a capital A, otherwise it'll look like the element sodium, and that'll be a little confusing. If you're still not quite have it memorized, then go ahead and always copy the number down until you get it memorized. So 6.022 times 10 to the power of 23 molecules, or atoms, or particles, or formula units. In this case, atoms. So now how do I do that on a calculator? Well, on most calculators there's going to be a button. I'll show you a few different versions of calculators. Here's a Sharp calculator, and on the Sharp calculator there's a button here, EXP, and this button EXP is a scientific notation button. If I turn the calculator on, notice what happens when I press it. So I'm going to go 6.022, and then when I press that EXP button, the calculator adds times 10 to the power of, and then I just type 23. So 6.022, press the EXP button and say to yourself times 10 to the power of, and then 23. On some Casio calculators, here's a Casio calculator, there's a button. This is not very common, but down here near the equal sign, there's a button there which instead of EXP, it actually says times 10 to the power of, and that's unusual. Most calculators don't say that. So 6.022, I press that button and it types in automatically this, and then I just say 23. Okay? Now the advantage of using the scientific notation button on the calculator is that the calculator then treats the number as a single thing. 6.022 times 10 to the 23 will be thought of as a single number instead of 2 numbers. Okay? Some people type in scientific notation as pressing the times button and then 10 to the power of, and that actually leads to some problems later on. So although it works sometimes, it doesn't always work. Here's a Texas Instruments calculator, and they have a very commonly seen EE button. So this EE button is their version of the EXP scientific notation button. So I would type here 6.022, then I press that EE button, and then 23. Alright, and that would mean 6.022 times 10 to the power of 23. On a computer, you would type 6.022 and then the letter E, which means times 10 to the power of, and then 23. A Casio calculator, one more time. This one at the bottom again has an EXP button like the Sharp calculator did. And finally, on a graphing calculator, the Texas Instruments TI-84, for example, their scientific notation button, it's a little hard to see with the light, but it's a second function, and it's this EE right above the comma button on the calculator. So here, if I turn on the graphing calculator, it's a little hard to see, but 6.022 and then second function EE, and on the screen it actually says the letter E and then 23. So that would be 6.022 times 10 to the 23. And again, the advantage is that the calculator treats that as a single number, not as two numbers being multiplied. So on your calculator, let's take 10 times 6.022 times 10 to the power of, that scientific notation button, 23. And you should have been able to do that with some mental math, but on the calculator we confirm our answer, 6.02. I'm going to keep 3 significant digits because 10.0 had 3 significant digits, times 10 to the power of 24 atoms of sodium. Okay? Now we'll go a little bit faster for the next few questions. All right, let's take a look at this question number 6. You have a test tube that contains water contaminated with lead, and we're told there's 8.5 times 10 to the 15 atoms, a huge number of atoms of lead in the water sample. Well, how many moles of water would that be? Now, just doing some mental math, we know that a mole of lead would have Avogadro's number, 6 times 10 to the 23 atoms. So although 8 times 10 to the 15 is a big number, it's nowhere near as big as a mole. So that means the answer, how many moles are there, is going to be less than 1. In fact, 10 to the 23, Avogadro's number, and 10 to the 15, this number, the difference between those would be 10 to the power of 8, right? From 15 to 23, so 10 to the power of 8. So I'm going to get an answer close to 10 to the power of negative 8, something like that. So there's some mental math. Let's jump in and solve it. So you have 8.5 times 10 to the 15 atoms of lead, and we want to know how many moles is this. So we'll set up a unit multiplier, we'll get rid of our atoms of lead, and we'll switch to moles of lead. The numbers here are Avogadro's number. 1 mole is 6.022 times 10 to the 23 atoms. Since lead is made of atoms, we have Avogadro's number of atoms. So again, using that scientific notation button on the calculator, 8.5 times 10 to the 15, divide by 6.022 times 10 to the 23. Now, if you're using that scientific notation button, there's no need for brackets. It'll work out perfectly just like I read it there. We press equals, and my calculator screen says 1.41 times 10 to the minus 8 is the answer. So equals 1.41 times 10 to the minus 8 moles of lead, which is pretty close to what we said it would be just using some mental math. Alright, so now let's try another one. Why don't we jump in and do question number 8. Okay, in this question you have an aluminum can with a mass of 50.0 grams, and we're asked to calculate how many atoms of aluminum are in the can and how many moles of aluminum are in the can. Okay, so how do we do that? Well, if you've got a periodic table, you can look up the molar mass of aluminum, and you'll notice that the molar mass of aluminum is 26.98 grams. So 1 mole of aluminum has a mass of close to 27 grams. Since this can is 50 grams of aluminum, then it's more than a mole. But it's not quite 2 moles, right? Since 2 times 27 would be 54 grams, this is going to be just a little bit less than 2 moles. So there's an estimate of the first answer, how many moles of aluminum. It's going to be a little bit less than 2. How many atoms of aluminum? Well, 1 mole of aluminum would have Avogadro's number of atoms, so 2 moles of aluminum would have twice that. So 2 times 6 times 10 to the 23 would be about 12 times 10 to the 23, or about 1 times 10 to the 24 atoms. So let's jump in and see how good those estimates are. So we have 50.0 grams of aluminum, and we want to know how many moles is that, so switch your grams to moles. Now when you see grams and moles in a unit multiplier, you're looking at molar mass. So you go to a periodic table, 1 mole of aluminum has a mass of 26.98 grams. So grabbing a calculator, 50 divided by 26.98 is, just like we thought, a little bit less than 2. We're going to keep 3 significant digits, 1.85 moles of aluminum. Now how many atoms is this? I'm going to take that answer we just got, 1.85 moles of aluminum, and now to find atoms we're going to use Avogadro's number like we were doing earlier. So convert your moles to atoms of aluminum. 1 mole is Avogadro's number, and I'll just say Ma this time, of atoms. So once you've done a few of these, you quickly learn that whenever you see moles and grams or grams and moles, it's a molar mass. All right? When you're seeing moles and particles, whether it's atoms, molecules, formula units, doesn't matter, you're using Avogadro's number in that unit multiplier. So let's get this answer, and we're expecting a huge answer, right? The number of atoms in almost 2 moles is going to be a huge, huge number, so it should be times 10 to the power of some big positive exponent. So 1.85 times 6.022, using that scientific notation button, times 10 to the power of 23, equals, and it's pretty close to what we said, 1.11 times 10 to the 24, and that's going to be atoms of aluminum. All right, so when you're counting how many atoms there are in a large sample, a reasonably large sample, it's going to be huge. If you're counting how many moles there are, you're not ever going to encounter an answer of 10 to the 24 moles. Moles will always be some number of reasonable size. All right. So question number 14 is a more practical experiment. You're doing a lab, and the lab tells you that you need 0.25 moles of sodium hydroxide. So how many grams should you use? In the lab, we measure out masses of substances. We don't measure out moles. So if you needed 0.25 moles, how many grams is that? Well, 0.25 moles, and again, pause the video and try it yourself if you think you know what you're doing, of sodium hydroxide. And remember, for me, I'm looking for not just the final answer, but are you showing the unit multipliers correctly with units, paying attention to sig figs, etc. So convert your moles to grams of sodium hydroxide, and if you're paying attention, you know that this, grams and moles, is a molar mass. But this time it's a molar mass of sodium hydroxide. So we'll grab a calculator. Sodium hydroxide has 1 sodium, 1 oxygen, 1 hydrogen. So we look at a periodic table. 1 sodium, 22.99 grams. 1 oxygen, 16 grams. 1 hydrogen, 1.01 grams. The molar mass of sodium hydroxide is 40 grams per mole. So 40.00 grams in 1 mole. So 1/4 of 40 means we're going to need 10 grams of sodium hydroxide. And I'll keep 2 significant digits in that answer because we had 2 significant digits in the moles. All right, so the next question, the density of methanol, 0.79 grams per milliliter. What volume of methanol should you use if you need 0.0125 moles of methanol in an experiment? So see if you can pause the video and try that yourself. Now we're going to need in this question the formula of methanol. We saw that in our nomenclature unit earlier. CH3OH is methanol. So if we need 0.0125 moles of methanol, and we want to know what volume, I guess we'll use milliliters since the density was given in milliliters there, we're going to need 2 unit multipliers, and although we could do it in 2 steps, I'm going to just do 2 multipliers side by side like that. So the first multiplier will convert the moles into what? Well, I suppose we could switch moles to molecules of methanol using Avogadro's number, but I hope you realize that's not going to be very helpful to find the volume. Instead, we'll convert the moles to grams of methanol, and that's a molar mass of methanol. So grabbing a calculator, we have 1 carbon, we have 4 hydrogens, we have 1 oxygen in the formula for methanol. So 1 carbon from a periodic table, 12.01 grams, 1 oxygen, 16 grams, and the 4 hydrogens, 4 times 1.01, 32.05 grams is the molar mass of methanol. So 32.05 grams for 1 mole. Now that I've got the mass of the methanol, we can switch to volume using the density. We can get rid of the grams and convert to milliliters because we were told in the question that there's 0.79 grams for every milliliter, and that's a density calculation. So now just double check, yep, the units work out nicely, grams cancel, moles cancel, and we're left with milliliters. So 0.0125 moles times 32.05 grams per mole and divide by 0.79, keeping 2 significant digits in the answer, 0.51 milliliters of the methanol should be measured out. All right, let's do one more, well, maybe 2 more questions here from this worksheet. Question number 18 is one that's going to talk about molecules of water. So you have a bathtub with 30 liters of water, 30.0 liters of water. How many molecules of water are in that bathtub? Now, the hint is to use 4 unit multipliers. I hope that you immediately realize that the answer to this is going to be huge. The answer is going to be times 10 to the power of some huge positive exponent, right? The number of molecules in 30 liters of water. Molecules are tiny. The answer is going to be huge. So let's start with 30.0 liters of water. And what could we convert that to? Well, the liters, I suppose if I convert liters to milliliters of water, I could then use the density of water, which I know is 1.00 grams per milliliter. Okay, now technically density changes with temperature, but we'll assume that that's the density here. So we'll get rid of milliliters and switch to grams of water. And now that we've stopped talking volume, we've now got mass in grams, we're now sort of home free, I hope. We can get rid of the grams of water and we can convert to moles of water using the molar mass of water. And then finally, with 1 more unit multiplier, I'll put it underneath, we can convert the moles of water into molecules of water. And that will be using Avogadro. So the first multiplier, in 1 liter, there's 1,000 milliliters. In the second multiplier, the density of water, grams per milliliter, it's 1.00 grams per milliliter. The third multiplier is the molar mass, grams and moles, molar mass of water, and that's 16 plus 2 times 1.01. 1 mole of water is 18.02 grams. And finally, Avogadro's number, 1 mole of water has Avogadro's number, Na, of molecules. So now I'm going to grab a calculator. And we'll type that in and we'll get the answer. So we have 30 liters. If we multiply that by 1,000, okay, so times 1,000, we've converted to milliliters. I don't need to times by 1 or divide by 1. That's not going to change anything. So this is how many grams we have. We divide by 18.02. That's how many moles we have. And now we multiply by Avogadro's number, so times 6.022. And we're using that scientific notation button, times 10 to the power of 23. And the answer is, not surprisingly, huge. The answer is 1.00 times 10 to the 27 molecules of water. A number that's so big, it's hard to wrap your brain around it. 1.00 times 10 to the 27 molecules of water. The next question on the sheet, number 19, how many atoms of hydrogen are in 36 grams of water? Well, if you've got 36 grams of water, you're going to have a lot of water molecules in there, and then each water molecule contains hydrogen atoms, and there's 2 hydrogen atoms, H2O, for every molecule. So the answer here is going to be huge, isn't it? It's going to be bigger than the number of molecules of water. So let's jump in. You got 36 grams of water. Convert your grams to moles of water using the molar mass of water. And now we can convert moles of water to molecules of water. And then finally, I'll squeeze it underneath, we can convert molecules of water to atoms of hydrogen. Okay, so let's see what numbers to put in those multipliers. Grams and moles of water is a molar mass. 1 mole of water is 18.02 grams from a periodic table. Molecules and moles, well, that's Avogadro's number. 1 mole has Avogadro's number of molecules. And then atoms of hydrogen and molecules of water, well, that's going to be the formula for water. Looking at it, H2O, there's 2 atoms of hydrogen for every 1 molecule of water. Now, there might be other ways to approach this. There's often more than one approach that will get you the right answer. So if you did this in a slightly different way but got the same answer with unit multipliers shown that are logical, then your answer is fine. So 36 grams, we divide by 18.02, so there's going to be around 2 moles of water. We multiply by Avogadro's number using the scientific notation button, and then we multiply by 2. So the answer is 2.4 times 10 to the 24 atoms of hydrogen are in the 36 grams of water. And the final example that we'll do here, be sure you've tried this yourself, don't just copy the answers. You've got 20.0 grams of aluminum nitrate. How many atoms of oxygen will there be? Well, again, just like we saw a moment ago, this answer is going to be unbelievably large, right? It's going to be a huge, huge answer. So let's jump in and try. So we have 20.0 grams of the aluminum nitrate. What will I convert that into? Well, we'll convert the grams into moles of aluminum nitrate using its molar mass, which we'll get from a periodic table. And then we can convert moles of aluminum nitrate into, well, you might be tempted to say molecules, and I'd forgive you for saying that, but remember that this is an ionic compound, aluminum nitrate. So it's really not made of molecules. So instead what I'm going to say here is formula units. And I'll abbreviate that FU formula units of aluminum nitrate. A formula unit is like a molecule, but it's not really the same thing. Ionic compounds are not made of molecules. Finally, we'll get rid of the formula units of aluminum nitrate, and we'll get what we wanted, which was atoms of oxygen. So now, we grab a calculator, we've got a periodic table in front of us. Aluminum nitrate has 1 aluminum, 3 nitrogens, and 9 oxygens. So, from a periodic table, 1 aluminum, 2698, 3 nitrogens, 3 times 14.01, and 9 oxygens, 9 times 16, 213.01 grams is the molar mass. So 1 mole, 213.01 grams. Avogadro's number, 1 mole has Avogadro's number of formula units. And finally, looking at the chemical formula, in 1 formula unit of aluminum nitrate, there are how many atoms of oxygen? Well, 9. We just said that. 3 times 3, 9 oxygens. So now, 20 grams, we divide by the molar mass, 213.01. We multiply by Avogadro using the scientific notation button, and then we multiply by 9 because there's 9 atoms of oxygen in every formula unit. We'll keep 3 significant digits, 5.09 times 10 to the 23 atoms of oxygen. So I hope that helps with some basic calculations. You can, if you made a lot of mistakes, not understanding some things, then make an appointment and come for some help one-on-one on this topic.